Okay, Assalamualaikum and very good afternoon. So today our lecture is about passive filter or analog filter, and this is going to be our last class. Okay, before I proceed with the passive filter, so let us look at a mathematical model of a system that you've been doing all this while, without you knowing it. Okay, so when I said about mathematical modeling of a system, it means that we have to derive a mathematical equation to describe the system that we are looking into. Okay, and then when we derive the mathematical equation for the system, so usually what we look at is the input and output relationship of the system, and usually we refer as a linear measurement system. And the equation or the general equation that usually represent this input and output relationship of a linear system is called, can be represented by the ordinary differential equation, or we call it ODE, where if you look at this slide, the left hand side is the order of the system as well as its derivatives. Okay, so derivatives of the output equal the order of the system with and its derivative with the coefficients, okay, of the inputs. So in this case, u is the input, y is the output, and u and y varies with t. Okay, where a and b are the constant coefficients. And when we want to analyze the system, what we usually do is we find the transfer function. What is a transfer function? The system output over the system input. Have you been doing or deriving the transfer function in your previous class?
In ODE, yeah.
Yeah, and what about the transfer function?
Not remember.
Not yet. Okay, or maybe you have been doing it, but you not realize it. Okay, okay. So that is a mathematical model in general. Why I have to touch it? Okay, we will see it later on in the slide. Okay. So the most important thing is the ODE, the input and the output, and the transfer function. Okay, so why we do this? Why we have to derive the mathematical equation of the system? Okay, usually what we have, for example, in your case, electrical engineering students, the most common system that you will be analyzing is the RLC circuit, right? So name it with any design, okay, either parallel or series, this components. And what I can give you for, because I'm familiar with the mechanical systems, or maybe you will be seeing it in your control class. Okay, for mechanical system, the components are usually what we did is we look at the force and um, the motion. Okay, so for example, in mechanical we have F equal to ma. So where the F side is looking at the total force that can make the system move equal to ma, and a is the accelerations. Okay, so in your case in RLC circuit, you're looking at the voltage, the current, along with the components R, L, and C, the common RLC circuit. Okay, so you define the system and its components, the voltage, the current, the R, the L, and C, and you get the physical law where you have, for example, in electrical, you have the Kirchhoff's law, you have the Thevenin's law, you have the nodal analysis and so forth, and you obtain the mathematical model, and um, you arrange it into the ODE. Okay. Next, what you've been doing for the first half of the semester, you're doing the Laplace transform. The Laplace transform is to simplify your mathematical model describing your system. And then you solve and then you look at the output behavior after you do the inverse Laplace transform. Okay, so this is what you've been doing actually. So if I can put it in summary, so first you have this physical model. So in this case, we have a RLC circuit, we have the input voltage, and then we need to find the output voltage with these RLC components arranged in this way in the series, and we have at the output is resistance. So what we did is using all those physical law of the electrical system, so we derive the mathematical. So KCL, you have the equation for the uh, current, for example. So in a closed loop circuit, the total current equal to zero. And then you define what is IS, what is IR, IL, and IC. So you will come up with these equations, which if you put it together, it representing the differential equation of that system, where you have the second order. In this case, your system is in second order. Okay, because you have d square v. Okay, so this is what we call differential equation. And then we linearize it using Laplace transform. So this is what we have. Okay, if we're looking at the output over input, we will come up with these equations. And then after that, we do the transformation, and then we look at the behavior in the time domain, just like we did yesterday. Okay, so this is the whole thing. The same things goes for mechanical system, chemical system. So first we start with physical model, mathematical model, and then we look at the ODE, and then we do the Laplace transform, Fourier transform, and then we analyze. So that is basically what we did. Okay. And then, okay, now let us relate what is the mathematical modeling, and in your case, the RLC and the transfer function. Okay, so just if you can't remember when you did the transfer function, so let us recap. So usually the transfer function, we do it in the S-plane. What is the S-plane? The one that you learned from Dr. Liza about Laplace transform. So S-plane is a complex plane on which Laplace transform are graphed in frequency domain. Okay, so S-plane is in frequency domain. It's just like what we did before when I described you the complex number, the real axis, the imaginary axis, right? Okay, so that is what all about the frequency domain. So why we need to know the frequency domain, or maybe for the mechanical system, why we need to have that? Because for example, in RLC circuits, or in this case, in what we're going to look at the RLC filters, have frequency dependent response because of our ZL and ZC. Okay, so when we do the voltage analysis, the voltage divider, just like yesterday, okay, we have to calculate the impedance. Okay, impedance in this case, impedance R is clear, XR equal to R. Impedance of inductor, ZL is J omega L, where omega is actually the frequency. And then capacitors, impedance for the capacitors will be 1 over J omega C. Okay, so when we have this and we transform the equations, okay, into the transfer functions, because we want to look at the output relationship over the input relationship. Okay, so that is the transfer function. Okay, output over input. So the output is the numerator, the the uh, the input is the denominator. And what we usually do, especially in the Laplace transform, you will convert into the poles and zeros. Betul tak buat kan? Class? Did you do that in your Laplace transform? Hello?
Yeah.
Okay, you get what are the poles, what are the zeros for that particular system or circuit. So the degree of your system, or in this case, in our case that we're going to look at later, is filter. It depends on the degree of denominator. Okay, for example, if you have x square for your denominator, meaning that your system is a second order system. Okay, so once you have the transfer functions, and then you do the partial fraction, okay, and then you solve for poles. Poles is the denominator, and zeros is the numerator. Okay, and then each fold, this one you will learn later in control engineering. So it means each poles will give minus 20 dB decade. Okay, so in order to have some idea of what is the input and output relationship of a circuit in a frequency domain, let us look this figure, figures 18.7. So you have the input just now, the circuit, the RLC circuit, okay, and then the output, and then you want to look at the relationship between the input and the output and the input, and we can define it using the transfer functions. Okay. Okay, for example, a very simple RLC circuit here. We have an RLC circuit with the voltage VI, maybe sine theta, sine omega theta, something. Okay, this is our input. And then in our RLC, we have inductance, inductor, capacitor, and resistor. So we want to look at with this input, with these components RLC, what is our output? So using the voltage divider technique, we can have, just like we did yesterday, we can have the output over input, which in this case, if we calculate or use a Laplace transform, we have this. For this particular circuit, output from the resistor, so it will be RCS over LCS square. So what order is the system, class?
Second order.
Second order, because our S here, 2. And then if we rewrite the equation, this is what I mean by the Laplace. And then we see that here, S square, second order. Okay. Okay, so that is regarding the mathematical equation. Why do we need to derive the mathematical equation of our system? And then we relate to the transfer function just now. Okay, and then I go specifically to the RLC circuits. So for you to have some ideas on the mathematical equations as well as the transfer functions, the output over the input, as well as the frequency domain, in this case using the Laplace transform. Okay, so now this is what we're going to discuss today, more on the filter, and particularly in this case is analog filter. Okay, so what is filter? Filter a circuit that is designed to pass signals with desired frequencies and reject or attenuate. Attenuate means reduce, reduce the signals, attenuate others. In this case, for example, I have we learn about when we talk about Fourier series, we have signals with different harmonics, right? Okay, so different harmonics, and then sometimes this harmonic representing noises. So we only want the main, for example, the main signal. So we want to reject the other two signals. Okay, we have F1, for example, F1 is 0.5 is the amplitude, sine uh, maybe 10 omega t, and another one F2 equal to 10 cos sine 20t and so forth. Okay, so we have a signal, so we want only the desired signals with a signal with the desired frequency. So we use filter. As a frequency selective device, a filter can be used to limit the frequency spectrum of a signal to some specified band. So here we have band of frequencies, not particularly one frequency, but maybe we want a range of frequencies. Okay, so when we talk about signaling, okay, and then we need for a certain band from maybe 20 to 30 kilohertz. So that is called band of frequency. So with this filter, we can have we can select the spectrum that we need, that we want to. Okay, so that the noises can be rejected or attenuate. Okay, filters are the circuits used in radios, TV receivers to allow us to select one desired signal out of multitude of broadcast signals in the environment. Kan semua orang dapat TV apa? Online TV, right? So when you choose a particular stations or particular signals, it's actually you um, playing with the value of the resistance so that you can get the particular frequencies that suits to that channel. Okay. So for filter, we have what we call passive filter and active filter. So in this class, we only look at passive filter. Okay, what does it mean by passive filter? Passive filter if it consists only passive elements which are resistant, resistor, inductor, and capacitor. Okay, very simple filter, passive filter. So what what about active filter? Active filter if it contains an active elements, for example, transistor, op-amp. Okay, so op-amp usually for integrator, differentiator. So adding in addition to the RLC. So you're not looking at the active for this syllabus. For this class, we only look at the passive. Only R, L, and C, and it will be arranged in different ways that you have learned in your elementary circuit theory class. And kadang-kadang ada series, sometimes we have RLC in series, sometimes we have RLC in parallel, sometimes we have combination series and parallel and so forth. Okay. Okay, talking about filters, there are four types of filters. Um, One is low pass filter. So low pass, as it names after, so it passes only low frequencies. So for example, we want only frequency from 0 to 10. Above 10, for example, 11, we want to attenuate or reject. So we can use low pass filter. So passes low frequency and the frequency higher, for example, 20, 10, 100 kilohertz will be attenuated or removed. High pass filter, as it names after, passes high frequencies and reject low frequencies. So we will look at the figures afterwards. And a band pass filter passes frequency within a frequency band. So there is a certain range of frequency that we need to keep and reject the others. So we use band pass filter. And what about band stop filter? So the two will be different. And if you can look at the figure, for band stop filter, it passes frequency outside a frequency band and block or attenuate frequency within the band. So let us look at the figure. Okay, so these are the ideal meaning that at cutoff frequency it will stop the signal. But ideally we cannot get that. Usually we have sort of like ada bengkok sikit lah. So ideally, kalau kita kata if you set ada low pass filter, so if you look at this graph is tengok H tu usually representing the transfer function, and in this case it is a magnitude because it is absolute value, okay, and then it is transfer function because it is H and W, okay, W meaning that it is a frequency, okay. And then if you look at from 0 to infinity of the omega, the frequency, so from 0 to omega c, so certain frequency that is cut off, right? So that is why we call omega c is the cut off frequency. Okay, so the signals will be 1 here, meaning that whatever that you send into your filter, you will get exactly the same, 1 to 1. Okay, sometimes we need to amplify, so therefore the value of this one will be 2. Let's say kita nak apa? We want to amplify the signal. Okay, so we have to calculate so that the value of the H will be 2 lah. Okay, so in this case, this is just a unit output. So whatever that you put into your filter, you will get exactly the same because of the value 1. Output over input equal to 1. Okay, so the second one is high pass. So it will stop frequency below omega C and only pass the frequency above that omega C, that particular frequency. And this is band pass. So we have a range of signals that we want to keep. Okay, and then, okay, ada orang masuk. And then for the band stop, Okay, so bandstop it only passes frequency above omega 1 and omega 2. So this is the summary of the characteristic of the ideal filter. Sometimes we design a filter, but we don't know is it a low pass, high pass, band pass, or band stop. We can look at the summary here. So if at the beginning your signal will get 1, but as the omega goes infinity, it will get 0. This is actually low pass. For band pass, initially it will be 0 and infinity. Later it will get 1, representing band, uh, uh, high pass. Okay, and then band pass 0 0, either starting or infinity, and band stop it will get 1 1 0 and infinity. So this is the summary, so that you have some idea what type of filter is that. Okay, any questions so far, class? Can I get some feedback?
Okay.
Understand?
Yeah.
Other?
For now.
Okay. Follow? Okay, follow. So let me proceed. Okay, so 5 parameters of a practical filter. So when you're designing a filter, so these are the things that you have to look into, because sometimes ideally we can have this type. Okay, so whatever, for example, low frequency, I need a frequency from 0 to 10 hertz, for example. So using this low pass, this ideal low pass filter, whatever that I put into that filter, I will get it exactly, kan? But then sometimes it is not, practically sometimes you cannot have that. But we can take into we can study what are the parameters that we can play with, or sometimes depending on the design. Okay, these are parameters, the one that we can change or manipulate, for example. So the first one is cutoff frequency, or FC, or sometimes omega C. The filter response leaves the error band. Okay, if you look here, so this is what we call cutoff frequency. So if the signal that you need, the spectrum is 1. So cutoff frequency is when your signal is at the 70% of the actual 70, minus 3 dB. So when it reach the 70% of the signal, so we call it cutoff frequency, omega C. Okay, stop band frequency of Fs, the frequency at which the minimum attenuation is reached, because sometimes we cannot get direct 0 here. It has some attenuation, but then there is a macam apa, what we call uh, a very small error that we can still accept. So this is some certain percentage. So that can be considered the stop band frequencies. Because if, for example, this signal keep on oscillating like this, so we cannot identify when it will stop the stop band frequency. So usually at certain, let's say if we declare it's 5% of the frequency, and then we calculate, so this is the stop band frequency, so we can identify what is Fs. Okay, pass band, a ripple A max, error band in the pass band response. So this is the A max, the attenuation, how much that we can accept. And then minimum pass band attenuation, minimum signal attenuation within stop band. So between the signal, the perfect signals into the frequency at which we declare as the stop band frequency. Okay. And then order of the filters, or the filter of the number of poles. So usually order of the filter depends on the poles, the denominator. Okay, second order, third order, and so forth. So when we derive our mathematical equation of our RLC circuit, okay, if let's say I give you a circuit of RLC, but maybe the C and the R is parallel, so you have to derive, and then later on you get the uh, system with the denominator s to the power of 2. So meaning that your system is your filter is a second order filter. Okay. Now let us look particularly, so that is filter in general. So now let us look particularly to the Passive. What does it passive mean just now, class?
RLC only.
RLC, yeah, no PAM, no active components. Okay, so we start with the low pass filter. So sometimes we represent as LPF, low pass filter. Low pass filter has a gain response with the frequency. If you look at the diagram here, so this is what it means. So for example, I have omega 1 and omega 2, and my cutoff frequency is somewhere in between. So after this input signal pass through the low pass filter, so you can see that the omega 2 attenuate, dia punya apa, amplitude reduce lah. Kita dah berjaya kurangkan dia. We can reduce that noise so that we have better signal lah. So for example, this one signal yang kita nak plus the noise. Okay, so we only want the output. So a frequency below the cutoff frequency gets a pass, and anything above it attenuate or rejected. Okay, and why at this one? Why it is rejected? Because the gain, this is called gain because output over input. Okay, the gain reduced to 0. Okay. Uh, if you look, how do we how do we design a low pass filter in terms of RLC? Okay, so this is the figure. We have here R and C. Okay, when I have R and C, so I try to get what is the output here. So using the voltage divider technique that you learn in your circuit analysis, so we're going to have this equation. Okay, so if you put into S the j omega, so we have 1 over S. RC is the coefficient plus 1. So meaning that our system is first order system. Okay, so when we have this is a RC circuit which gives the low pass filter. Why it is low pass filter? We will look at the example. Okay, so in low pass filter, we just said just now that at 0, the gain or the transfer function is 1, and later it will turn into 0, infinity. And when we set the cutoff frequency is the half frequency power, meaning that it is 70% of the actual signal. If our signal is 1, when the signal start to reduce 70 at 70.7%, it is where the cutoff frequency is. After that, the signal start to attenuate. And how can we calculate that? So we equate the magnitude of transfer function with our equations, and we can find what is RC. In this case, omega C. Omega C is 1 over RC. So only frequency up to the cutoff will pass through the this filter. Okay, so this is what I mean by ideal. Kalau tengok kat sini, ideal is okay, cantik je, but actual there will be some reduction here. That's why we need the 70 or cutoff frequency at 70.7 here, or in dB it is actually minus 3 dB. Okay, so let us look one example. Okay, so I will go to Jamboard. Kita ada C, so it is a low pass. Low pass, remember low pass we have R and C. So let me go to the Jamboard. So we have our input. Okay. So we have the input. Okay, so this is our low pass. Berapa tadi R dia? 47. I think we did it yesterday. So this is 47 nanofarad, and then this is 47 kilo ohm, I think. Low pass filter. Low pass filter. Okay, what is the question? Uh, Sinusoidal, calculate the output voltage. Okay, copy here. I don't know whether it works or not. Paste. Alamak. Tak. Okay, never mind. So what it needs is output voltage at F equal to 100 hertz. Okay, so V out. V out at F equal then kilohertz, 10 kilohertz. Dia tanya cutoff frequency ya. Okay, so how do we start class? Any idea? Eh, any idea?
Tu
So V out tadi macam mana? V out equal to
voltage divider.
hmm?
Guna voltage divider.
Okay. Cuba. Everyone, please try. Using the voltage divider, so it will be the capacitive inductance, which is X C over R plus XC, right? Ini voltage divider, and then times dengan V1, VI, sorry. Okay. So is this value, please find your impedance. So what is our XC? 1 over J or 1 over 2 I, because we are dealing with frequency. So let the first one, our frequency is just now tadi 100 hertz. So what is our XC? Nano tadi, nanofarad. Nanofarad 47. So class, what is our XC and what is our V out? Ada siapa calculate tak? Banyak kita baru lupas je ni. We have more. Anybody calculate what is the output voltage?
Punya XC
Nano minus 9 ah. So berapa?
33
33 kilo.
0.86 kilo ohm.
0.8. Okay. Yeah, kilo ohm. Okay. Kilo ohm. Okay, kilo ohm. And then V naught? 10. 10 kan? 10 volt tadi, right? Kali dengan 33 point. Bukan. Cool. Thirty-three times 33.8 times 10.3 and then over. So you calculate the R square, square root of R square and C square. Okay. So ada siapa yang dapat? Anybody has the answer for this? Based on my calculation here, the value is 9.9. Is it? 9.9 volt V. Maknanya ada 0.1 reduction lah. Betul? So meaning that you put here 10. Can someone please turn off the... Siapa yang tak mute tu? So this case we have 10 volt here. After this filter, our output is 9.9 just now, 9.9 voltage when the frequency is 100 hertz. So now let's calculate the same thing. The only difference is the impedance value when our frequency is 10 kilo. 10 kilo kan? Yeah, 10 kilohertz. So I suspect sini 10 to power 9, 100 to power 3. Then 3, 4. So it will be about minus 4 lah. So kalau sini 3, 3, 8. Okay, kilohertz 1. Okay, so potong lah. So about 33, betul? Our XC? Plus? 33, 300. Gan? Can you give me the answer? 7.82. So this one is for what? Ikai? Salah. Okay. So Salah calculate for this one. Just now the 10 kilohertz. Macam mana boleh salah tu? 10 kilo will be 10 to the power 10 kilo, 10 to the power 4, and our C just now is 10 to the power 9. So 5 lah. Okay, 10 to the power 5, 4 dengan. Okay, so go back here. So 10 power 4 divide 2 by time 47. So dapat berapa? 338. Okay, good. What about our voltage class? 338.6. 338.6. 338.6. What about our voltage now? If you can look here, this is lower frequency, this is higher frequency. Okay, Chua, berapa voltage output? You should have, I suspect, reduction of the voltage because it is a higher frequency. What is the voltage? Daniel, are you here? Daniel? Daniel?
Yeah.
0.07. Daniel dapat apa? 0.07. Any more? Chua pun dapat 0.072. So about 0.07 volts. So what can you conclude here? This is when frequency 100 hertz, lower frequency. So your signal maintain. If you put one just now 10 volt, so we have 9.9. And then 10 volt here for 1K, we have ada berapa? 0.07 after passing through this low pass filter. Okay, so this is what it means, the reduction there. It's not totally zero, okay, but then ideally it will be zero, but usually it will be very difficult for us to get zero. Okay. Okay, so I go back. So just the solutions here, 0.07. Oh, mine is 0.0, not 0.07, 0.718. So please calculate and please check. Never mind, we will check. Macam mana tadi 10, 10 and then 33. Can someone check this one? Is it a 0.07 or 0.7?
Doktor, dia punya R tu 47K ataupun 4.7K?
Okay, check balik 47K. So saya buat tak salah Okay, now I know the answer. Okay. 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 So 9.9 tadi betul?
Tak dapat juga. Tadi saya dapat 5 point apa.
Something. Yang lain? Lima point something.
Sama 5 point something.
5.8 macam tu lah.
Okay, 5.8 maknanya kat sini is okay, change that. Not kilo, 4.7. Sorry. Because the solution is 47 kan. 4.7 kali. Ya. Dia tak dapat nanti. So now you get the answer? Tapi sini bukan kilo, right? 47 is 40, no, but then 47 kilo. Where is my 100 there? Here. Hmm. So if it is 4.7, the answer for the XC also will be different, right? Okay, never mind. I will check later.
Yeah.
Okay. Okay, so if we calculate the cutoff frequency, so it seems that by RC 4.7. So the cutoff frequency is 720 hertz. Okay, so at 720 hertz, the output voltage is 77 point of the input percent of the input voltage. So that is what it means by low pass filter. So you have the idea for the low pass filter class. Okay, so I only give you examples for low pass. Okay, then let us look the circuit for other types of filters. Okay, so this is the concept of high pass filter. So if we have two signals here, the omega frequencies with the amplitude equal, let's say equal to 1 here, after passing through the high pass, the lower frequency will get attenuate or reduced or rejected. Okay, so the circuit for the high pass filter, the voltage will be the output of an RC is taken off at the resistor. So therefore, when we do the transfer function, the H omega, we will have this equation. Okay. And then when we do plot the spectrum magnitude, we will have something like this. Okay, so that is for the high pass. Remember the circuit, the output at the resistor. What about band pass? Band pass here, we only pass the frequency within the band, and the other two will get reduced. So it is actually for band pass filter the combination of the low pass and high pass. Okay, because this is the high pass and this one is the low pass. Oops. Okay, the combination, if you look at this diagram, this is the high pass, this is the low pass. So when we have the circuit, it will combine, it will be the combination of the RLC and the output is taken off at the resistor. Okay, salah ni. Let's see, resistor. Okay. So our transfer function for band pass will be here. Okay. When you do the mathematical, okay, let me double check the filter. The RLC, the band pass. Okay. Yes, the band pass is at the resistor. Okay, the final one. So this is how it looks like, ideally. Actual, actual versus ideal. And the cutoff frequency will be 1 over square root L and C. And the band stop, okay. So the band stop is low pass and high pass. And this is a combination here. But it is either this one and this one. Then we pass. Okay, so the circuit for the band stop or band stop filter will be RLC, but the output is taken off at C and L. So that's why our voltage here for the numerator will be inductance and capacitance. Okay. So this is how it looks like, actual versus ideal. Okay. So now let us look at the last example here. We have this circuit and it is a filter. So we need to determine what is the type of filter. Is this one? Is it a low pass filter, high pass filter, band pass filter, or band stop filter? And with the value of R and C given, determine the cutoff frequency. I forgot to give the value of L. Okay, let's say everything we stick to 2. L kilo ohm and L equal to Henry. Okay, so how do you start class? Do you have any idea? Hello? Is everyone here? Answer. Okay. Okay, let me redraw that one in our Jamboard. So just now we have input voltage. And then we have our inductor, 2 Henry. And the voltage just now, it doesn't give us the value. And then we have the resistor and the capacitor. This is the input. This is R just now is 2 kilo. 2 kilo. And the capacitor is micro. C equal to so this is our output. Okay. Okay, so determine what type of filter. So you want to know whether it is high pass, low pass, band pass, all the different 4 types of filter. And then cutoff frequency. So first actually here in solution, first actually we have to determine the transfer functions. And then it gives us here the cutoff frequency is 242 radian per second. And later on, please convert it into hertz. Okay, so you have to do the transfer function output over input. In this case, you have to solve this first. Okay, and then get the transfer function. So if you want to make it simplify the calculation, if you use J omega, it will be messy with the J and the omega. So you can change it into S. Okay, I give you 10 minutes to try. Please try to get at least the transfer function. You've been doing this right for your circuit theory class. Betul tak? Macam mana nak dapatkan ni? You have to do the parallel and then the series, right? Am I right? Class?
Yeah.
Okay, so do that. Parallel with the C is 1 over J omega C or SC. Z1 lah. Okay, we name it as Z1. So what will be the impedance here? Tadi. Okay. What is the value, class? Is everyone here? Aina ada? Is it R? 1 plus what else? SRC, is it? Betul tak?
Yes.
Okay. And now that you have now that you have this one is R over 1 plus SRC. Now you calculate. I just need to know what is the output over input equation. Anyone finish? So let's say we make it L first. Not putting the number yet. Okay, so make it L. Standardize. It's L. Okay. Anyone finish with the transfer function for this particular circuit filter? We want to look at the final transfer function for this one. So the output is here. Okay, anybody? No one answering my question? I think I will give you this you to do during this weekend then. And from this transfer function, we will know whether it is a first order or second order system. Class, are you here?
Yeah.
Okay, so what is your transfer function? RBB here. R So I think I should get something like S square plus something like S, and then plus something like, I don't know, RLC, R. May I know the coefficient? It is a second order. Jauh tak nampak.
RLC.
RSC. I need to know the transfer function, Aina. So now that we have from this, we reduce to this one. Okay, R and C parallel, so we have R over 1 plus SRC. Now combined with L, L is SL, right? J omega L.
R over RLC S square plus SL plus R.
Okay, hold on. So this one is LC, right? Or RLC?
The first
Aina?
is RLC, second is L, and last is R.
L, and then this one is R. Okay, what about the other? Do you get the same answer with Aina? Same answer? Ini si answer to yang ni. Yes, okay. So we get this one. So now convert it into omega. Because we want to go back to the questions. Cutoff frequency. So we need the omega. So when we convert into omega, S into omega, so it will be S square is J omega square. So J omega square is minus, right? Minus omega square LCR and then plus J omega L, then plus R. Okay. And the question asks us determine the cutoff frequency. So how are we going to determine the cutoff frequency? What do we know about the cutoff frequency previously, class? Okay, let us go back. The concept of cutoff frequency. This one. Okay, the half power frequency or cutoff frequency is when magnitude of the transfer function equal 1 over square root 2 or equivalent to 0.707. Okay, so now go back to this one. So you have to put it into 0.707 or 1 over square root 2. Okay. Based on this equation, so you know the value of R, right? You know the value of L, you know the value of C. So can you find the omega class? Okay. So you should get omega. Please calculate. Based on the solution just now, it says the cutoff frequency is 742 radian per second. And then please convert it into hertz frequency. Okay, what about one of the question did ask us what type of filter is it? Is it a low pass or high pass or band pass? How do we determine? We have to go back to this table. Okay. What does this table says? Okay, so we look at the two conditions. When we put our omega equal to 0, what is the value of our H? And when we put our omega equal to infinity, what is our H? So from there, we can um, know what type of frequency. So go back here. Uh, what happened when our omega equal to 0? Is the value 1 or infinity? And what happened when our omega equal to infinity? Based on this equation class. Anyone?
H0 equal to 1.
1. What about infinity?
Zero.
0. Okay, so let me highlight it. So which category of filter this one falls into? 1 and 0. Low pass. Okay. So this is a low pass filter with a second order system. Okay. So second order low pass filter. Okay. So omega cutoff frequency just now, the answer is 247, right? 742. 7 cutoff frequency C 742 radian per second. Okay, so is it clear, class? Okay, sometimes you are asked to design either a low pass based on the requirement of your circuit, whether you want to pass the high frequency or low frequency or a band of frequency. So you have ideas of how to design your filter, and then with the cutoff frequency specified, being specific with the omega naught or omega c, so you can play around with the value of R, L, and C. Okay, so I think that's about it for filter. So okay, tepat 3:30. So we finish everything. So good luck everyone for your test one on Thursday, right? Thursday evening. All the best to you. And if I want to discuss or to have more on the demo for MATLAB, I will either call a class or I will record and share in our Google Classroom. Okay, because one of your assignment, which is assignment 3, is on analog filter using MATLAB. Okay. Any questions so far? So most of the material are from Alexander and Sadiko. Okay, if you don't have any questions, I think we call it a day today.